It's Wednesday, right? Lose track of what time it is. So looks like we're getting close to the holidays, and maybe some people have already taken off to go home for the visit. I always thought we should move Thanksgiving. I mean, school has been set up because, you know, why we have our timings we have? 100 years ago, most of us was farmers, so we have to go do the harvest. Everything was based around the harvest. How many of you are farmers? My grandfather was a farmer. My mom lived on the farm, but I'm not a farmer. So anyway, why don't we move Thanksgiving closer to Christmas and then just keep going and get like done a week earlier, maybe 2 weeks earlier, right? I think, but maybe we need this little time to kind of, I don't know. Anyway, we're here, so we're going to move forward. What I'm showing you, we're in Module 7 now. Today we're doing the definite integral, and you'll see there's only 2 modules after that. So we'll do those after the test. I set up a new, actually it's not new, it's the old module where we did the review for 4.1 to 4.4. So I just moved it down, and in here I've added the part of the review that's for 4.5 to 5.2. So just what the 2 we've covered today, 2 previously. And remember, 4.5 is really just problem solving based on the earlier stuff. So this exam is much more compact as far as techniques and what we're going to be doing. So I think I would expect that you'd be able to do better than before, or at least the same or better. So that's the hope. And then that'll propel you, give you a little bit more confidence as you go into the final. And remember that final, do well on that. If it's higher than a previous grade, it will replace that previous. So we just take that exam score and put in the final score, which is going to be higher. If it's not, then don't worry about it. But it should be. Okay, that's the goal. So those are here. So Friday we'll kind of go through 4.5 to 5.2. I'll come back 4.1 to 4.4. I do have a copy of the exam now, so I'll review that so that in the review I will focus on the types of questions that are on the exam. We'll make that focus. But again, we still have content to do today, so we'll go ahead and do that. And then we'll have, so Friday's well, let's just go ahead and get into the PowerPoint because it's got everything. So today we're doing 5.2, the definite integral. And what we're going to do is we're going to bring together what we did on Monday with the area under a curve that was sort of a preliminary, and tie it in together, not quite yet, but tie it in with the antiderivative. Or at least set the foundation, the basis for bringing in that antiderivative. And so shortly after the third exam, we will definitely tie in all those parts, and we'll find the easiest way to find the definite integral. But today's, again, more about understanding what the definite integral is and what it's giving us so that it helps us get there. So we are, let's see. So we're going to be here today. Friday, we've got an exam review. We come back, we've got the test. 5.3 is going to be very closely tied to what we do today in 5.2. We've got the Thanksgiving holiday. Again, if you're traveling, that's fine. We'll have the recording. Come back, we've got that last week. We just got one section. We got 2 days of review as needed. We've got a whole week to review because our final isn't till Thursday night, like late, right? But it's a common final, so that's how they do it. What we will do is we'll work in a retake of that mastery test, maybe sometime during that last week before finals, maybe during finals. We'll find a good time that accommodates everybody who wants to take it. Again, the best way to sort of prepare for that is just kind of keep up with what we're doing now. If you want, go back to the mastery test review, some of those things. I will make a new test, but what it will be is here's a function take its derivative. And it'll be sort of just open answer, just do it. Show the work or don't show the work, but just have the right answer, or a right answer, because I think that was part of the problem, is the answers that were given were done in a specific way that wasn't necessarily the way I would do them either. So we'll just, any way you get there, get me a correct answer, and we'll do it that way. Okay, so 20 questions, just like, same rules as the other one, except it won't be multiple choice. Similar type derivatives, and we'll be all good. And same rule, if you get 18, then you get 100%. 18 or 19 or 20, you'll get 100%. Okay, so today we're going to talk about a Riemann sum, which is sort of what we were doing on Monday, but they didn't specifically call it that. So we're getting the area under a curve, and we're using rectangles to kind of estimate that area. As we get into that, I've got some technology. If you have a TI 84 or 83 calculator, it'll work. I'm going to show you some links. If you have the TI Inspire, they might have it, but it's a program that we'll download, and actually I'll use it here. And the reason I use it is because not only will it give you the answer to a Riemann sum, but it will show you a graph of what's going on. There's only 3 questions on the homework. Well, you could actually also use this for the previous homework, 5.1. But there's 3 questions on the homework where they have you do Riemann sums, and we'll walk through kind of that by hand, but I'll show you that the calculator will also do it, and it'll show you what's going on. And then the rest are really the properties of integrals, which we'll go over today as well. Okay, so a Riemann sum is just, we're going to have a curve, some function, and what we're trying to do is estimate the area between the x-axis and the curve. Any area that is above the x-axis is considered positive. Any area that is underneath the curve or below the x-axis would be negative. And again, think of this as accumulation. And remember, this is the function we're dealing with is a derivative function. It's a rate. It's a rate of change. So if you have negative rates, you're losing stuff instead of gaining stuff. So it gives you sort of the total that you would accumulate over this time period. So you're subtracting, if you're negative, it means you lost some money, right? So that's coming off of their profits. You made some profits here, you made some losses here, but then you made some profits. So anyway, it's a way of going to calculate of what has accumulated. And again, it could be about profit and loss, could be about water coming in, going out, whatever it is. But that's kind of the concept we need to know, is that area above the x-axis is positive, area below will be negative. And again, that comes directly because the function we're working with is a derivative. Okay. So how is a Riemann sum related to a definite integral? Because today we're going to call it a definite integral. It's really not too much different than what we were doing on Monday, and we didn't call it a definite integral. But it's more getting into the notation. So in this notation, we're relating, this is kind of what we did, is we made rectangles. We found the area of each rectangle and added them together. So that was a summation. What we're saying is that the definite integral, we do the same thing, but that's what this little S looks like. It's really for sum. That's what we're doing. Here is where we have our boundaries, so we're going from point A to point B. So they'll list those points of, the interval we're integrating over. So from maybe 2 to 8, one of the examples we'll do, we find all the areas. There's a connection between the dx, that's reminding us it's a derivative that we're dealing with, right? And it's directly related to this change in x, which is a rate of change, right? Change in x, how x is changing, the size we use that was our width of our rectangles. And then we got the height of the rectangle from the function value itself. We plugged in an x value, we got a y value, that was the height of the rectangle. So the change in x was the width, the function value at either the left end or the right end or the midpoint, that was our height. And when we multiply those two, right, height times width, or length times width, whatever you want to call them, that gave us area. And then it gave us area of each of the rectangles. We got all those areas, we added them together, and that was our estimate. Okay. And what we're going to do is we're now working with it more and more in this form, because what we're going to see is that this is actually the limit if we were to let those rectangles to put in an infinite number of rectangles. They would be very thin, there'd be so many of them, and it would be very accurate. Okay. So that's the idea, is we're moving towards that. And we're going to find that when we come back, that the connection with the antiderivative is we'll find the antiderivative of the function we're given, and that we'll use that from the boundaries, and it actually give us the area exactly. Kind of cool. Not necessarily obvious, that's why we go through all of this, but it will. We'll do it by checking. And I'll show you a little bit today, because we'll use the tools we have that have some built-in things and such. So we've got just sort of this theorem, so we'll go through a few of the, we won't try to prove these or get deeply into it, understand how to use sigma notation. We'll go directly to the graph and say, this is how we do it, rather than trying to understand all the notation, because we're only doing this for one day, actually just 3 problems, so we don't have to really worry about understanding the stuff that's supposed to be the buildup, but we'll understand how to do it. So there's this theorem that if the function is continuous on this interval from A to B, then, or it could have what they call jump discontinuity, so it stops here, it goes here. We can fix that. Basically, we go from this point to this point. So we basically, as long as it's continuous, or just has a few jump discontinuities, which we could kind of work with, then we're going to be able to integrate it. We're going to be able to find that area under the curve. Okay, and again, remember that was sort of what was required for a derivative. So if we have a derivative function, it has to be continuous. Otherwise, it doesn't exist there, right? So it's just more rules that say, okay, if this stuff happens, then it's going to work. There we go. So then, how do we use Riemann sums to approximate a definite integral? Again, this kind of will take us right back to Monday's lecture. We're going to use the same sort of techniques, but we're going to give you a few hints, formal hints of how we do it. So first of all, you'll be given a definite integral, and that's what this is the definite integral. It says we're going from an x value a to b, so these will be numbers, right? The way we find out how wide our rectangles are, right? So there's, remember we were drawing a bunch of rectangles, and we had our change in x down here. We did it so that the change in x was always the same, because that made the calculations easy, and usually we did that at the end. Well, if you take the limits, a to b, you subtract them, that gives you the distance between a and b, right? So an example, if we're going from 2 to 8 of some function, the way we find out the width of the rectangles is we take 8 minus 2. That gives us our distance, which is 6. And then we divide that by however many rectangles we want to put in there. Okay, and the homework problems, they'll tell you use 3, use 4, use whatever. And again, the idea is the more you use, the more accurate you'll get. So let's say they said use 3, we would divide by 3, and then that tells us all of a sudden that each rectangle is going to have a base of 6 divided by 3 is 2. Let's see, start doing this. Sometimes it's my arithmetic that goes off. I get those answers. Anyway, here we are. So we're going to have rectangles of width 2, and we'll have 3 of them. And then now what we got to do is either get where are we hitting the function? Is it the right point, or is it the left point, or is it the midpoint? And then we plug those values into the f of x. Now this one's going to be, so every 2, so we know we would have on this interval x is equal to 2. Did I get that right? 8 minus 2 is 6, right? 6 divided by 3 is 2. Okay, doubting myself here. So we've got 2, going by 4, 2, 4, 6, 8. Oh yeah. And then remember, since we only want 3, if we're doing a left-sided, we would use 2, 4, and 6 as our x values to plug into the function. So we would find f of 2, f of 4, and f of 6. Okay. If we wanted the right side, or if they asked for the right side, and on the homework they asked for both, then we would be using 4, 6, and 8, the right sides here. So then we'd look up f of 4 plus f of 6 plus f of 8, and they'll give us the function. And then if we wanted the midpoints, which ones would we look at? We'd look at halfway between, right? So those we have to do a little bit more calculation, but this is not too bad. Between 2 and 4 is 3, between 4 and 6 is 5, and then between 6 and 8 is 7. So those would be, we'd look up f of 3 plus f of 5 plus f of 7, and those would be the 3 heights of the 3 rectangles. And then again, they're always, all of these are multiplied by the change in x, and all of the change of x is 2. So again, we could do this calculation and then multiply this by 2. We could do this calculation, multiply this by 2. We could do this calculation over here and then multiply it by 2. Okay, and we would get an estimate for the area under that curve, whatever the function they gave us. Now, I'm going to show you, I've got, again, if you got the program, which I'm trying to get done a little bit early, because if you have a TI-84, I've got a cable, I can actually just copy this over to you in about 5.6 seconds. We'll time it to see if it, but anyway, a short time, I can get it into your calculator, you'll be able to use it. I'm going to use it during this lecture to show you how it works. There's also, if you don't have a TI calculator, I'll show you there's a way to download it and have it on your computer like I did. I just figured that out today. It took me about 45 minutes to get it all working, but it works. So we'll do that. And again, that's what this is sort of saying is each of your x values is, again, you start at the one end, you start at A. In this case, the example I gave was A was 2, right? This is A. And 8 would be B. And then you, what you're doing is A plus this gives you your xi. So you figure out your x's plus the change in x. So and our change was 2, and then we did 2, 4, and 6. So it gives us our endpoints one way or the other. So that's what all the notation is. But again, when you go to do it, we're doing it with small enough values that it should be, don't worry, don't let the notation get in the way. Let me put it that way. So we'll do a few of these. Again, before we get too much into this, just remember area could also be negative. So you might want to, if you're going to do this by hand, you might want to look at the graph first. And you might want to see, is it always positive? And we'll do a few examples where it's actually, there is some that's negative, and you calculate that separately, and then you subtract it from what you got when you got positive. Okay, so we kind of have to do, when we're doing Riemann sums, we have to do this segment differently than we do this segment. And so we have to locate these places where the function crosses the x-axis, right? Because when it's above the x-axis, it's positive. When it's below, it's negative. So again, it's good to do that. The nice thing, the reason I have that program is it will graph it for you. So it's kind of like you just enter it in, it'll graph it, it'll show you everything that's going on. You follow along, and then as you're following along with the calculations it's doing and what you're seeing, I think the goal is that it will do it quicker than you could probably do it on your own, save you some time, but then that allows you to explore it a little bit more and maybe get a deeper understanding, hopefully. Okay, so this is just saying take the positive values and then subtract the negative values, the negative areas from there. Okay, so we're going to, let's see, I'm going to walk you a little bit through. So there's this, if you download or if you go to the slide deck, I have a few links in here, and I'm just going to walk you through a couple of the things. So this is a website that's been around for years, It's not done by TI calculators themselves. It's some organization that basically just has been a repository for everybody. Anybody, you can upload a program. So if you make a program, you can upload it, and a lot of people have been doing. They've got a lot of resources. Let me put it that way. The one that I used is, let's see. So we're going to go to archives. That's where most stuff is. Where did I? Let's see. Now I'm forgetting. I think I went to, yeah. Let's see. There's a lot of information here. Let's see, services, basic, let's see. Calculators. So they have a lot of stuff about calculators. I want to show you, they have emulators, so that's what I'm going to be using to do this so that it's right on my computer. And now, services, oh, I think it's over here, so I just got to hide this thing, programming. So if I go to programming, they have different emulators, and where are they? Emulators. There's supposed to be a list here. Third one down. Oh, there. Emulator software. Okay, so here's the list. I downloaded the one. They have one Windows, Mac, and Linux. The one I'm using is CEMU. So you download that one. You need what's called a ROM, a read-only memory. You can, if you have a calculator, they walk you through how to download it from here, because that's the copywritten part of these calculators. The software anyone can make the software, but the ROM is copywritten. So if you download it from an existing calculator, then they're not violating copyright laws that way. If you don't have one, they have a way where you can go to some place and download it. That's maybe a gray area. But anyway, you can follow through. But that was kind of the hardest part. That's what took me a little bit of time. But you could do that. Anyway, you just kind of click on this link. You'll download it. The other thing you'll need is from TI itself. They have a Connect software, which allows your computer to connect to the calculator, and then you can download programs. Where I got this program, I also have it in Canvas. The file that you need, so you don't necessarily need to go here. If you have a TI calculator and you have the TI Connect software, you just go to Canvas, download the file, and it loads in real quick. Or if you have it with you today, we'll get you set up. But I want to show you this because this may be helpful for some of your other classes. So you could go to either 83 or 84. They have, depending upon what brand you have, you can go to the basic, and then where do we go? We go to math. Now, if you're in science, they have some science programs. They have various other things. I'll just go to math. They have all these different things. They've got trigonometry, statistics, linear algebra, finance, all these things, calculus. Okay, so they've got all these programs that are built for calculus stuff. I pulled one here on Riemann sums, and that's the one I'm going to use today, but they have some calculus packs with other programs. If you're motivated and you want to do some of these, again, I find that they actually help you understand things, because if it graphs it and gives you the answers and shows you through it, it's a nice process to go through. And that's the one I ended up last night downloading about 5 different programs before I found the one that really did what I want. Some of them just gave you the answer for a left bound or a right bound, which, okay, that's great, but I wanted it to show you, and it took me a while to remember which one did that. Okay, so that's just kind of, it's there, use it. If you're in chemistry, there's a section for chemistry, there's physics, there's thermodynamics. They have programs for, and again, these are just people like you and me, well, maybe not like me, but some of you who do some programming, they program it and upload it for us, and it's some pretty cool stuff. So with that said, let's come back. Oops. Let's come back to our presentation. So in the module 7, I do have this little thing. I've got the program here. You can just download that. Here's the TI Connect, a link to get the TI Connect software, which is needed to transfer from your computer to the calculator. And then, of course, you also need the right cable. This one's for going between 2 calculators. There's another one that you might have for your charging that has a USB to your calculator, and you'll be able to download them and really take advantage of the power that you have in the programming part of your calculator. Okay. So I thought what I would do is let's just go the first 3 problems in web work. I'm going to just work through them with the emulator. So we're in 5.2. And the first 3 problems all use, so that's pretty clear. And then let me introduce you. If you download that one program, the emulator, you get a little computer version. And what I like about this is you can change the settings, you can change the color, whatever mood you're in. I felt like purple today, so I went with purple. I had bright pink in the morning when I wanted to wake up. Whatever you want. It's just, and again, this is all free. And I'll just show you, if you do use this, once you have the calculator, what you do is from your computer, you have the file for the program. You just go up to File and go to Open. And I have downloads here. There's the file that I'm going to be using, Riemann 2.8. I just clicked on it, it uploaded it to my emulator, and now my emulator actually has the same program as is on here, okay? And so that's what you would do, okay? So what we're gonna do first is we're gonna go to Program. Oh, shoot, it disappeared. It was there, so maybe I'll need to do it again. Let's try this again. Sometimes these are always sort of quirky. So I just uploaded it into here. Evidently, when I close the program out, it disappears, but now I got it back. So kind of have to have it there sometimes. So we're going to do the Riemann program, which is number 1. And I hit the program key. That gets you up. And this is the only program I've got in here. You hit Enter, and notice it goes Program Riemann. You have to hit Enter again. And then it does something weird, and then you hit Enter again, and it starts to work. I thought, oh, it didn't work, but let's see if it did. So on it'll work. So what it's going to ask us to do is put the function in first. So come here. And so we just enter this as, again, using this keyboard, 4x squared plus 3x plus 4. That's all we have to do. We hit Enter. It's going to ask us for the lower bound, which on the integral, you'll see we have a 2 to 8. So I'm going to put those in. So I just put in 2 and 8. Ask for how many partitions. Down in the instructions, they say n equals 3. I'm going to do n equals 5 so that I don't give you the answers so that you can, it's not a big deal, right? But I'll show you how it works. I'll do 5 partitions. Hit Enter. And then what it does is it's going to draw the graph. It resizes the window to the size of your boundaries. Does that and shows you where 2 is and where 8 is. Not necessarily on the marks, but and then it says press Enter. Watch what it does. Now I can do a left, I can do a right, I could do a midpoint, I could do all of these. So the question's asking us to do a left and then a right, or right and then a left, so you'll be able to do both of them. So I just go down to number 2 if I want the left sum. But this is the cool part. It actually draws it in there, and it's a lot faster than I could draw, right? And I didn't have to do all the calculations. But then not only does it draw it, but it gives me the answer. That if I use 5 boxes, I'm going to get 6.3 or 636 is the area under the curve. Okay, we see, is that an over or an underestimate? Slightly under, right? Because there's some, it's when we use the left sum, we're slightly under. We hit enter again because then it asks for a right sum. We could just go do the right sum down to number 3 or enter number 3 on the calculator. And it does the right sum, which gives us a larger number, 946. Is that because it's over, right? Because we see parts of the boxes are going over the curve. So it's an overestimate. And again, if we took the two and averaged them, we'd get a better estimate. Usually more accurate. Okay? So far we good? Okay. Anyone want this program? No? No, you don't need this. You got it. Okay. Oh, yeah. Inspire should have one, but anyway, we'll see. What I want to do is I want to show you, because there's another thing we can do. We'll do the midpoint, and there's a slide in here that basically says the midpoint is like the best estimate you can get, 783. And I did this earlier. The actual area in there, I think, is 786. So 783 is pretty accurate. And that's just with 5 boxes. That's not that many, right? And actually with 3, it came up pretty close to that too, with the midpoint. So we're going to see what we've just done is maybe more, in a more convincing way, it proved to me that the midpoint is the best one to do. There's one more on here that we aren't going to ask you to do, but it's kind of cool that it is here, the trapezoid sum. And who knows what a trapezoid is? It's a rectangle that has what? The top isn't necessarily, it's not like a square, it's not 90 degrees, so the top can be, well, we'll just take a look, right? So number 5. So those are trapezoids, and you would think that that's more accurate, but it actually isn't, right? Because the midpoint is sums above, sums below, so it seems to equal it out. It's actually better. I was thinking trapezoids, how you look at that, doesn't that look pretty accurate? But it's not as accurate as the midpoint. So, and again, it's really difficult because do you know the formula for finding the area of a trapezoid? I don't. I have to look it up. So we look it up, and it's kind of funky, and because you got basically a triangle at the top and a rectangle. It's a lot of work, and it's still not as accurate as that midpoint. So that was kind of cool, I thought. And then let me just show you, if you don't have this particular one, we can quit this. So we'll go to 7. And then I'm going to go to y equals. So the cool thing is it actually, when we put the function in, it actually put it in y equals. That's how it was able to graph. The only thing is it doesn't have it chosen or selected to graph. So when you come back and you want to play with it, you go to the equal sign and hit enter. It will graph it now. And I'll show you. It's actually went in and it changed the window size, so we still have the same window size. I'm going to show you we have a tool under Calc, Second Calc. So you already have this. This is built in, where you can actually find the integral. This is going to be exactly accurate, okay? Because it's going to go, it's like, a million rectangles or whatever. And this is built in, so it's a built-in feature. And this is where we're going to go eventually anyway. And then it asks for the lower limit, same type of thing, 2. The upper limit, 8. And then it fills it in. You're going to see, I think it's 786. Exactly 786. So you see that midpoint was very, very accurate. Okay, with even just 5 rectangles. 3 was still, I think it was 784 with 3 or something anyway. It's very, very accurate. But we can do this. The thing is when they ask for the Riemann sums, if you give them this answer, even though it's more accurate, it's going to say, no, that's not right. We wanted 3 boxes. We want, So that's why the program will be helpful. It'll save you some time. And again, it gives you this idea. But the reason we're having you do this is to understand what we're getting is area under a curve. And again, if you can see it, it'll convince you, it convinced me more than any kind of mathematical proof, which the book has. It's filled with that, a couple pages of it, and all this notation and stuff. But a picture, to me, I understand it clearly. all the proofs, okay, so abstract. And again, if you were math majors and that's the field you're going to go into and you're going to do proofs, maybe that's important. But you're engineers, you want to understand the concepts so that you can use them. Okay, so that's the tool that I'm going to offer for you, and we'll just keep going with that. So you'll see there's that problem. The next one, this one is going to ask for right endpoints and then left endpoints with a different function. Again, same thing, just input it, have it draw it. They want 4 boxes. Again, if you're going to do this by hand, remember you take the, let's see, let me make it bigger again. You know, for this one, you would take your endpoints, it's 8 and 4, right? So you would take 8 minus 4. They want 4. 8 minus 4 is 4. So the width of each box is going to be 1. Okay, so you're going from 4 to 8. You're going to have a width of 1, so you're going to have this box and this box and this box and this box. It's just a width of, and your widths are all 1. Then you're going to be able to figure out what function values you want. So again, you could put this in your y equals, do a table, get the left sides, get the right sides, and you can do it. Again, if you've got the calculator, it just does it. Okay. And then there's only one more problem in the homework that's going to ask you to do that again, and it's going to ask for the midpoint rule. And again, if you've got the calculator, just do it. If you don't have the calculator, let me make that a little bigger, it's hard to see. Again, what you'll do is the same thing. You find how many boxes, right? They want n equals 4. So we do 3.5 minus negative 0.5 divided by 4, number of boxes, right? So that gives us 3.5 minus this. That's actually going to be 4 over 4. So our width of our boxes are 1. That makes the math really nice. And then what boxes do we want? Well, we're starting at negative 0.5. If we're going to have a width of 1, that takes us to 0.5. And then a width of 1 would be 1.5. Another width of 1 would be 2.5. Another width of 1 would be 3.5. Right? And if you know, whichever sin, we'd have a box there, 1, 2, 3, 4. Okay? But what we want is the midpoint. So we have to go halfway between each of these, right? So what we're going to want is f of 0, right? That's halfway between negative 0.5 and 0.5. 0.5 to 1.5, we want f of 1. We would want f of 2. And we then want f of 3. Okay? You add all those together, multiply them by the change in x, which is 1. That'll give it to you. Okay, so that's, and again, you could do it without graphing, but I like, yes?
Why do you use only 4 numbers and not keep going?
Because n is equal to 4. Yeah, because they told us to use 4. And so actually you end up with 5 numbers, right? The boundaries, the 2 endpoints, and then the 3 in between. But you get, it'll allow you to make 4 rectangles. And then the whole key is which function value do you use? Do you use the left end or do you use the right end? This one wants you to use the midpoint, so you use the midpoint for the height. And you're really just doing height times width. You're getting rectangles, area, and you're adding all those together, and that's, again, that's going to be very accurate. And again, I did this one with the program, and it comes out so close. You do, and then again, that's the nice thing with the calculator. You can switch over to the native calculator program, get the exact value, and you'll see your midpoint is very close to this. Okay, and we're almost done. Actually, we're going to take a look at the properties next. Let's delete those off because afterwards, all of these problems kind of get into more conceptual type things of integrals. Okay, you won't be able to calculate these, but we'll talk you through, and just have to kind of go through a few of these. Oh, there is actually, before I said that, one more we'll calculate, but we can't use the calculator. So there is one more system where they say just use the area. Because sometimes the graph, one of the graphs is a half circle, so you have to know the formula for finding the area of a circle, and you'll get it exactly. It's not using Riemann sums. We're going to evaluate this one in terms of areas. What kind of function is this? What? Modulus. Absolute value. Yeah. So it's an absolute value. And if you remember what an absolute value looks like, it's a V shape, either up or down. And this one, since it's got a negative, it's going to be a V shape down. So that gives us sort of like a triangle. Okay. And so for these, you actually have to go. You could use your calculator. You could also use Desmos. I find Desmos really easy to work with, so we're going to do that. The calculator you could do, but again, you're going to need to find where does it cross the x-axis, because there might be some of the area that's negative. So for this reason, I'm just going to go to Desmos. It's easier to understand. If this is on a test question or something, also practice with your your handheld calculator, maybe afterwards. So what was the function? It was 7? What was it? 6 minus absolute value of x, right? And I think I can just do this. Yeah, I can do that. So that's our graph. I guess I could put in f of x equals or something, or y equals. So that's our graph. We want the area from, let's go back. We want the area from -7 to 7. So I'm going to kind of write on this. So here's -7. Here's +7. So notice we're going to have a little bit of negative area. And then we want from here to here, we're going to want this sort of area in here. Okay. So how do we calculate this little area? And again, I could click here to see where my x-intercepts are. It's at 6. So at -7, what's the base? This little piece. 1. It's got a triangle that has a base of 1. What would be the height? Looks like a height of 1. It's going down, right? And again, what you'd have to do is either look at a table of values or click on it. See when x is 7, y is -1. So I've got a triangle that's got a base of 1, a height of 1. So I'm just going to draw that little triangle here, 1 by 1. It's a right triangle, so my area is just 1/2 the base times the height, right? 1 times 1 is 1. 1 times 1/2 is going to be 1/2. And since it's below the x-axis, it's going to be negative, right? So I just kind of, okay, that's a negative part. Got the similar one over here, and it's exactly the same. And this, you're going to have one very similar to this, but it's a little bit different size, so you'll do that. I changed it slightly. So over here, we could do the same calculation, so that's going to be -1/2. So we're going to have a -1, right? Let's see. Make sure that is. How do we find the area of this big part here? Well, -6 to 6, the base is 12. So that's the base. The height is 6. Okay, so 1/2 the base times the height. Base is 12. Height is 6. We can cancel there, so it's really 6 times 6. That's 36. That's its area. So we get 36 minus a half if we think that we found those 3 different areas. So the 35, right? Okay, so we didn't have to use Riemann sums because the shapes were specific shapes we could get the area of. If we used Riemann sums, it would be less accurate. So sometimes we can do this. You'll see there's one in there that gives you a circle. Again, just graph it, you'll see it. How do you find the area of a circle? Pi r squared. Okay? So a couple of those, and then we get into the properties. And I guess I have a hard time going fast, but let's see. Let's come back to this, and then we got our important rules. So these I'm just going to, these come right from the textbook. They're kind of right here. There's a couple of them that they will give you something that's similar, and you just sort of need to use these properties. Excuse me, folks. We just need to use the properties to come up with things. So we have this midpoint rule. We sort of use it. Again, there's a change in the boxes, and then, you know, if you're using the midpoints, you go halfway between your 4 or 5 boxes that we did. So we've kind of already applied this. Here's one rule, that if you go from B to A, that's the same thing as going from A to B, except it's negative. So direction would change positive to negative. Okay, so it is a directional accumulation. If you go the other way, it's considered negative. That's one property. Also, if you try to find the area at a point going from A to A, it's 0, right? You can't. A line has no area. That's all it's saying. A point has no area. So that's what that one is. These properties are just kind of more generalized. You can work with things. There's a couple of them you'll need to use. So if you're adding 2 functions together, you could do them separately, right? You can, if you have a constant multiplier, you can take it out and just at the very end, and we've been doing that. If you subtract, you can do it separately. Okay, so these work. So that's what it's just saying. You can do this. They're not necessarily, in math, we can't just obviously do it, but they've gone through and proved that it works. So I let other people do the heavy lifting. Just tell me what works, and then I'll do it. Okay. These ones are the ones, there's a couple of these that we're going to use. So let me spend a little bit of time, especially this last one. There's a problem in there, and it's maybe not obvious, but let's go ahead and see how this one works. So this number 8 is saying that if the function values, the function itself, if we know that it's limited between two values, m and n, so we'll put some numbers in here to make it more. So let's say it's somewhere between 4 and 8. That the function values are at least 4, but they're no bigger than 8. If we know that, and that's what occurs between our 2 endpoints, then what it's telling us is then we know that the integration, the area, will be between the b minus a, which would be our base, right, times the lower end, in this case 4, and at the upper end, it would be 8 times b minus a. So that what it does, it says, okay, since 8 is the biggest, let's just calculate what if they were all 8, a constant function. That's the biggest it could be, right? If they were all 4, that's the smallest it could be. So we've got the smallest and the largest, and we just know it's somewhere in between. And again, sometimes when we're doing things, we just need a ballpark. This theorem allows us to do a ballpark. But it's just sometimes the notation itself gets a little strange. Then comparing it, if one function is always bigger than the other function on that interval, then the integral will always be bigger than the other function. Okay, kind of makes sense that, if the y values are bigger, we're going to have more area there. So that one's kind of intuitive. Also, if the function is greater than 0 on an interval, then, which means the y values are positive, right? We're going to get some area, and the area is going to be positive. because if it's always positive, you can't subtract, you can't get negatives. Okay, so that's just what the properties say. These are the only ones we're going to need, and the last few problems, that's what you're doing, is you're applying these. So I think it should come pretty smoothly. We could look at a few of those on Friday if you'd like, but give it a try. I think that's all I have for today. Yeah, it won't let me go any further. That's it. So if you want to get a copy of the program, come on down. Oh, no, you might use them for manipulating them, but I don't, as I look through the problems, they're just more, we'll use them probably when we go to do the manual. So just, try to remember, but you go to link, you're going to receive, I'm going to send the program, remit. And then now when you go to program, and receive already. Send program, remit, transmit. Perfect, you got it. Link, you're going to receive, send, remit, transmit. Link, receive, send, it should. This one doesn't have.
I can just follow the basic.
Okay, yeah. Receive. Send.
You join class?
Thank you.
Well, I have to work on well, it's like a thing.
Send. Program. Transmit.
Yeah, just show up and
You got it.
you should
Thank you.
see it. You're welcome.
Going to receive. Going to send. Oops. And then transmit. Done.
Thank you.
Oh, I know how.
What? Alright. It's good.
Going to receive. I'm going to send.
It's pain in the ass. That's but today's not good.
Remit.
is that the plug-in might not fit into your calculator. I think you have a different one.
Yeah, in fact, I wish I would have held him back because that's a great calculator because it can actually go to an 83 as well as because you've got both connectors. You've got this one, you've got a cable that goes there. Actually, I got one of those. I loaned it out